Hello everyone, myself Dr. Ranjith Kumar. I'm an associate professor working in Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. Today, we are going to discuss the triggering methods and the dynamic characteristics of the SCR. In the last class, we have already started to discuss the triggering methods, and in the previous class, we have discussed already the forward voltage triggering method as well as the gate triggering method. So, and in this today's class, we are going to discuss the remaining three triggering methods, which are dV by dt triggering, temperature triggering, and the light triggering. So, when coming to the dV by dt triggering, okay, so how we are going to turn on the thyristor by using this dV by dt triggering. So, as we know, in all the triggering methods, the common point is we are applying the forward biased voltage across the anode to cathode, which means the anode is positive with respect to the cathode, so that the junction J1 and J3 are the forward biased junction and the junction J2 is the reverse biased junction. So, to allow the flow of current from anode to cathode, so we must get break down the junction J2 so that the flow of current is flow from anode to cathode. So, which means it is the turn on or the conduction mode of the SCR. So, to break down the junction J2, we are following the different methodologies. So, in the previous class, we have discussed the forward voltage triggering, okay, how the junction J2 is get breakdown by applying the forward voltage, and in the second methodology, which is the gate triggering method, so how we are using the gate current to break down the junction J2, so that also we have discussed in the previous classes. So in this class, for the same thing, we are going to do by dV by dt. So here what is mean by dV by dt, which is the rate of change of voltage. The dV by dt is the rate of change of voltage. So here, as we know, in the reverse biased junction, the junction J2 behave like a capacitor because of the space charge present at the junction J2. Then what is mean by space charge? That is, the space charge is nothing but the electrical charge distribution over a region or a space. So which means there is a charge distribution across the junction J2. So that's why we can consider the junction J2 will behave as the capacitor. Then, as PN junction has a capacitance, so the large the junction area is the large the capacitance. As we know, the C is directly proportional to the cross-sectional area of the capacitance, right? So that's why here the capacitance will increase by increasing the large the junction area, so that the capacitance of that particular capacitor will increase. So that if you apply the voltage ramp across the anode to cathode, then the current will flow in the device to charge the device capacitance according to this relation, which is IC is equal to C into dV by dt. So here, if you want to increase the capacitor current IC, what you have to increase? You have to increase the dV by dt rating, which means when we are increasing the dV by dt rating, the capacitor current will increase, so that the charging current becomes large enough and the density of moving current carriers in this device induces to switch on. So which means here we are increasing the capacitor current by increasing the dV by dt, okay, so that the density of the moving current carriers in the device induces to switch on. So in this way we are going to switch on the thyristor. But this type of dV by dt triggering is not suitable or not desirable because of the high charging current may damage the thyristor. High charging current may damage the thyristor. So that's why this is not desirable, and this is not the method that we can use to turn on the thyristor. The triggering is nothing but to turn on the thyristor. Then the next triggering method, which is the temperature triggering. In this temperature triggering, so how we are going to turn on the device by using this temperature. So similarly, in this case also, the junction J1 and J3 are in the forward biased and junction J2 is the reverse biased. And another thing, during the forward blocking mode, of course, we have discussed in the the operation of the SCR, in that operation of the SCR, and we have also discussed the characteristics of the SCR. So in that, we know the different regions, that is the forward blocking region and the conduction region and the reverse blocking region. So during the forward blocking region, most of the applied voltage appear across the reverse biased junction J2, because in the forward blocking mode, still the SCR will not turn on. So still the SCR in the turn off position only. So during the forward blocking voltage, okay, whatever the voltage that you have applied across the anode to cathode, so mostly most of the applied voltage will appear across the reverse biased junction J2, and this voltage across junction J2 associated with the leakage current, right? Because as we have discussed, there is a leakage current. Even though the thyristor is turned off, of course, when the thyristor is turned off, there should be no current flow. But even though when it is in the turn off, there is a small current will flow, that is called a leakage current. And because of this leakage current, the temperature may rise in this junction. In which junction? Junction J2. So which increase in temperature, okay, the leakage current through the junction J2 is further increases. Okay, which means here both, vice versa. Like by increasing the by the leakage current, with the leakage current, the temperature may increase, and because of the increase in the temperature, again the leakage current may furthermore increase. So that again, because of the leakage current furthermore increases, then the temperature will furthermore increase. So like that, at a particular point, at a particular temperature, or this cumulative process may turn on the SCR at some high temperature, right? So this is also not desirable method, because of the high temperature triggering may cause the thermal runaway, which means the thermal runaway means because of the high temperature, the device may get failure. So that's why this temperature triggering is also not advisable or not desirable to turn on the thyristor. And the next methodology is the light triggering. So because in the temperature triggering, with the help of temperature, we triggered, which means we turn on the thyristor. And in the dV by dt triggering, with the increase in the dV by dt voltage, so we turn down the thyristor. Similarly here, by using the light rays, okay, or the light particles, we are going to turn on the thyristor. Then how, here we are going to discuss. So in this method, the light particles, which means it is having the photons, okay, are striked in the reverse biased junction or near to the reverse biased junction. Because as we can see here, the structure, the internal structure of the SCR, so PN layers, and having the three junctions. So as we know already, because we have applied the forward voltage across the anode and cathode, so that the junction J1 and J3 are the forward biased and junction J2 is reverse biased. So we have kept a slot, okay, we have kept a slot which is nearer to the junction J2 to to strike or to induce the photons into that particular layer. So then when we are induced or when we are strike the the photons in the reverse biased junction, so which increases in the number of electron hole pairs, and because of that region, the junction J2 may avalanche, okay, so that the thyristor will get triggered, which means the thyristor will get turned on. So here for striking the the photons, okay, to strike the photons on the nearer to the junction J2, so we must made a slot, or we can also slot in the inner P layer. So if the intensity of this light thrown on the races exceeds a certain value, then the forward biased SCR is turned on. So in such a thyristor is known as light activated thyristor. So those thyristors which are turning on by striking the photons on the inner P layer, so which kind of these kind of thyristors are called as a light activated thyristors or light activated SCRs. Because when you are increasing the intensity of the the light, then it exceeds it, intensity of the light, so that then the increase in the number of electron hole pairs. Okay, so at a particular instant, or at a particular intensity of the light that we are throwing into the inner p layer, then at a particular point the thyristor will get into the forward bias, and which means it will turn on. Okay, so such kind of thyristors are called the light activated thyristors, and mostly these light triggered, the light activated thyristors are used in the high voltage direct current transmission systems, which are HVDC transmission systems. So these all are about the different types of triggering methods. Anyway, so as we have seen the different types of triggering methods, so how we can turn on the thyristor by using the different ways. Okay, so based on that, we have divided the different types of triggering methods. So when in all these triggering methods, so the most efficient triggering method is the gate triggering method. So in our further modules that we are going to use the gate triggering method to turn on the thyristor. So this is all about the different triggering methods of the SCR. So the common point that we can observe from all these triggering methods of the SCR is, so if you want to trigger or if you want to turn on the SCR, you must apply the forward biased voltage. The forward biased voltage is nothing but the anode is positive with respect to the cathode. You must apply the forward biased voltage across the anode and cathode. And the second thing is, of course, in the various ways we are just getting breakdown the junction J2 to allow the current flowing through anode to cathode. That forward by applying the forward biased voltage, that we are increasing, by increasing the forward biased voltage. And the second case is by injecting the gate current to the P layer, okay, which is because the gate signal is connected to the inner P layer, and then by increasing the temperature, and by injecting light particles, which are the photons, into the inner P layer, or by increasing the dV by dt. So in all these ways we are in all these methodologies we are applying to turn on the thyristor. And next we are moving to the next topic, which is the dynamic characteristics of the SCR, or which are also called as the switching characteristics of the SCR. Before, we have discussed the output characteristics, or we can also call as VI characteristics, or we can also call as the static characteristics of an SCR, and these are the dynamic characteristics of an SCR, or the switching characteristics. So usually the switching characteristics of the SCR is the time variation of the voltage across its anode and cathode terminal, and the current through it during turn on and the turn off process. Which means during the turn on and during the turn off, so how the voltage across the anode and cathode terminals are changing, as well as the current flowing through the SCR is changing. So which means the performance of the SCR during turn on and during turn off process, which are called the switching characteristics or the dynamic characteristics of an SCR. Here there are two different types of switching characteristics are available. One is turn on switching characteristics, another one is the turn off switching characteristics. The turn on switching characteristics means the characteristics during the turn on process, and turn off switching characteristics are the switching characteristics during the turn off process. And before going to discuss about the switching characteristics, okay, so are the turn on characteristics. So first we will discuss the turn on switching characteristics, then after we will discuss the turn off switching characteristics. So first let me discuss about the turn on switching characteristics. So as we discussed before topic, that is the triggering methods. So in the triggering methods, we have also discussed the gate triggering. Okay, so as I told you, the gate triggering is the most popular triggering method compared to all other triggering methods which we have discussed in the previous section. Okay, so there are two conditions to turn on the thyristor. One is you must apply the forward biased voltage. Okay, we must apply the forward biased voltage across anode and cathode, and you must give the gate signal so that the thyristor will get turned on. Right. So then the thyristor turn on time. Okay, so how we can define the thyristor turn on time, which means the turn on time of the thyristor is defined as the time required by the SCR to change its state from the forward blocking mode to forward conduction mode when a gate signal is applied. This is called the thyristor turn on time. The thyristor turn on time is because, as we have discussed, the different modes of conduction of the SCR. Okay, one is the forward blocking mode, and then after forward conduction mode, then the reverse blocking mode is there. So the forward blocking mode, okay, I mean, because in the forward blocking mode means we are just initiating to turn on the thyristor, and once it is turned on the thyristor, then it will come to the forward conduction mode, which means then the time required by the SCR to change its state from forward blocking mode to the forward conduction mode is called as the thyristor turn on time. Of course, maybe in this in this time, okay, so the characteristics may not be same. So that's why here, to understand better the characteristics during the turn on time, we are dividing these characteristics into three regions. One is the delay time, another one is the rise time, and the third one is the spread time. So how, I mean, what is delay time and what is write time and what is spread time, that we will discuss one by one here. So here you can see the switching characteristics of the thyristor. Okay, so here there are different curves that you can see here. This curve is representing the VA, that is the anode voltage, which means the voltage across the anode and cathode, that is the forward biased voltage which we are applying. Okay, and this line represents IG, that is the gate current. Okay, and next here it is this curve represents the anode current. Okay, because these are the three important parameters which related to turn on process. Because if you want to get turn on, the conditions are, you must apply the forward biased voltage, which means the VA, and you must give the gate signal, and which means the gate current. Okay, so which means there is a minimum gate current required to turn on the thyristor. You must apply the minimum or the gate current which must be above the minimum gate current required to turn on the thyristor. So that's why here we have considered the gate current signal also, or the gate current waveform. And the anode current, so the role of the anode current is, okay, so not only you just need to apply the forward biased voltage, or the the gate current is greater than the minimum gate current required to turn on the thyristor. Okay, so you must apply the gate current, the forward biased voltage, unless the anode current reach the latching current. Okay, so we also discussed what is latching current. The latching current is nothing but the minimum current required to turn on the thyristor, or the minimum anode current required to turn on the thyristor. Okay, so when the anode current reaches to a latching current, okay, so then only the thyristor will get into the turn on. So up to that point, up to that extent, you must apply the forward biased voltage. Okay, and another thing is, anyway, the gate current also you must apply. Of course, there is a minimum gate current you must give to turn on the thyristor, because in the gate triggering method we have discussed already why we are increasing the gate current. Right. Okay. Then here, first the delay time. So if you want to turn on the thyristor, you must apply the forward biased voltage. So that's why here we are applying the forward biased voltage. Right. Then also you must give the gate signal. So that's how here we are giving the gate signal. Gradually we are increasing the gate signal. And which means up to this point, okay, so let me consider here it is T1. This first signal is T1. This is T1. So up to T1, the thyristor is not turning on. Okay, just we have initiated to turn on the thyristor. Right. So that's why during this time also there is a small current which is called as a the forward leakage current, which is called as the forward leakage current that we have studied in the VI characteristics, which means still it is in the forward blocking mode only. Still it is in the forward blocking mode. Then the delay time is measured from the instant at which the gate current reaches to 0.9 Ig to the instant at which the anode current reaches to 0.1 Ia. Okay, which means here at this particular point the gate current reaches to 0.9 Ig. Okay, which means here Ig is the minimum current required to turn on the thyristor. So suppose let us consider 10 milliamperes is the minimum current required to turn on the thyristor. So here 0.9 Ig means the 9 amperes. So the 0.9 Ig2 where the gate current reaches to 0.1 Ia. Again here Ia is the minimum current required to turn on, the minimum anode current required to turn on the thyristor. So suppose in this case also some 10 milliamperes of the anode current is required to turn on the thyristor. Then 0.1 Ia means just 1 milliampere, that is 0.1 into 10. Because here Ia and Ig are the final values of the gate and the anode current. Ia is the final value of the anode current and Ig is the final value of the gate current, which means the Ig is the minimum gate current required to turn on the thyristor and Ia is the minimum the anode current required to turn on the thyristor. That is how. Okay. Then of course there are many definitions are there for the delay time. So one is with respect to the anode current and the gate current. So with respect to anode and gate current, it is the time required to reach the gate current from at instant the gate current 0.9 Ig to the instant at which the anode current reaches to 0.1 Ia. So which means here this region is called the delay time. Here the delay time that I have indicated with TD, and it is also it can also defined based on the anode voltage VA. So it is also defined as the time during which the anode voltage falls from VA to 0.9 VA. So because here it is VA at this instant it is VA, and at this instant it is 0.9 VA. Here VA is the initial value, which means initially we will apply some voltage across the anode and cathode, the forward voltage. So whatever the initial forward voltage we are applying across the anode and cathode, that is the value of VA. So here you must remember the Ia and Ig are the final values and VA is the initial value, because Ia and Ig we are starting from 0. Okay, but VA we are not starting from 0. Initially we are applied some amount of voltage across anode and cathode, that is the forward voltage. That's why that is the initial value. Okay, so that's why here I have mentioned VA is the initial value of anode to cathode voltage when the SCR was in the forward blocking mode. Right, and it is also defined, it is the time in which anode current reaches to 0.1 amperes from the forward leakage current. Because up to this point, this is the forward leakage current. Okay, so the time taken by the anode current reaches from forward leakage current to 0.1 of the 0.1 Ia, that time is called as a delay time. So this initiation of turn on process basically starts from gate to cathode junction only. Because we have already discussed in the gate triggering method. Okay, so as soon as we apply the gate current, our charges are injected into the gate to cathode junction, then the thyristor will turn on. So the turn on time of the thyristor will depends on the amount of gate current that we are supplying, right? So this is about the delay time. So which means we are initiating to turn on, which means we must apply the forward biased voltage that we are applying, and you must give the gate current that we are just gradually we are increasing the gate current, because there is a minimum value that must reach the gate current to turn on. And another thing is the anode current. Of course, anode current also, when you are turning on, means you are just initiating the turning on process, so which means the anode current must be increased, okay. And there is a minimum current required to turn on the there is a minimum anode current required to turn on the thyristor, so that's why the anode current also gradually increasing. Then next, rise time. So here, as I have indicated, the rise time is, with respect to VA, here the rise time is this 0.9, in this region, and with respect to IA, it is in this region, okay. And with respect to what is that, IG is also there. Rise time is defined as the time taken by the anode current, to rise from, because with respect to anode current, which rise from 0.1 IA to 0.9 IA, that is called the rise time. So the time taken by the anode current to rise from 0.1 IA to 0.9 IA is called the rise time, because during this time it is rising, the anode current is increasing. And with respect to VA, that is the anode voltage, the time taken by the anode to cathode voltage drop from 0.9 VA to 0.1 VA. So this is called the rise time. So as we have discussed again, of course the gate current IG, okay, so is will affect the turn on time of the SCR, So of course the turn on time is nothing but TD plus, that is the delay time, plus the rise time plus peak time. So especially these rise time is depends on the gate current. So more the value of the gate current, then lesser will be the rise time, which means the anode current will reach to the minimum anode current required to turn on the thyristor very fastly, okay, because of increasing the more value of the gate current. And another point that we have to remember is, so during this rise time, the current and voltages are more. That's why the turn on losses of the SCR more during this time, because here the third waveform, which represents the power losses, because anyway during the turn on also you will get some power losses, which are called as a switching losses. During the switching also you will get some losses, which are called as the switching losses, right? So here the power losses that you can see, so this is during the delay time, but during the rise time you can see the power losses are more, because of the anode current is high during this time, right? So this is the another point that we must remember during this rise time. So the rise time can be defined with respect to IA and with respect to VA. With respect to IA, the time taken by the anode current to rise from 0.1 IA to 0.9 IA, and with respect to the VA, the time taken by the anode to cathode voltage drop from 0.9 VA to 0.1 VA. So here, as you can see, the rise time is inversely proportional to the magnitude of the gate current. Yes, of course, because as we can see, if you are increasing the gate current, then the rise time will get decreased. So that IG is inversely proportional to TR. This is about the rise time. Next, the spread time. Okay, so which is represented by TP, or we can also call it as a peak time or spread time. Okay, so here this is the the TP, that is the spread time. It is also we can define with respect to what is that IA. So the time taken by the anode current to reach from 0.9 IA to IA, 0.9 IA to IA. So after the spread time, the anode current attains the steady state value and the voltage drop across the SCR terminals becomes equal to the on state voltage drop. So usually this is also we have discussed in the the output characteristics of the SCR. So the on state voltage drop of an SCR is in the range of 1 to 1.5 volts. 1 to 1.5 volts. Because as we can see, another point here is the higher the value of the gate current, lesser will be the turn on time. Because especially in this turn on time is nothing but it is a sum of the delay time plus rise time and peak time. So in this delay, when compared to delay and peak time, the rise time is more depends on the amount of the gate current which we are applying. So that's why in generally, how much gate current we usually apply is 3 to 5 times of the minimum gate current required to turn on the thyristor. Which means, let me consider here some 3 milliamperes is required to turn on the thyristor. But to increase or to decrease the turn on time, we usually give 3 to 5 times of the minimum gate current required to turn on the thyristor. Which means here the minimum gate current is 3 amperes. So we will give usually 3 into 3, 9 to 3 into 5, okay, 15. So in between 9 and 15 amperes we will give to increase the, to decrease the turn on time of the device. So when the gate current is several times higher than the minimum gate current required to turn on the SCR, then that SCR is said to be hard filed or overdriven SCR. Overdriven SCR. Because of course what is mean by this driven period of the SCR that we will discuss in gate characteristics. Okay, so overdriven SCR that we usually call as. Of course, even though to increase furthermore, we are not allowed to give or increase the gate current, okay, beyond the 3 to 4, or 5 times of the minimum current required to turn on the thyristor. Of course, there is a maximum limit is also there. Like the minimum limit, there is a maximum limit is also there. So you must operate the gate current within that limits, okay, to turn on the thyristor. Otherwise, the thyristor may get damaged. To avoid that thing, we must operate within the limits of the gate current. So this is about the peak time. So the total turn on time can be defined by the the sum of the delay time and rise time and the peak time. So that this is the total turn on time. So which means after the spread time, the thyristor will get into the conduction. So that's why you can see the voltage is dropped to 0.1 VA, that is on state voltage drop, which means so after this the thyristor will get into the conduction mode. So that's why you are getting some constant load current, and because it is the thyristor is turning on means it is get short circuit, then the voltage is around 0. But of course, it will not get into the 0. Still, there is some voltage that is called the on-state voltage drop across the SCR. This is about the turn-on process or the turn-on characteristics. So, what is the behavior of the the anode voltage, and what is the behavior of the gate current, and what is the behavior of the anode current that we have seen during the turn-on process. Next, the turn-off characteristics or switch-off characteristics of the SCR. So then what is mean by the turn-off time? The turn-off time is the time taken by the SCR, okay, which transit from forward conduction state to forward blocking state. Forward conduction state to forward blocking state. Because in the forward blocking state, again it is turning off. So which means the process is initially it is a off state. So first it will get into the, if you want to turn on, first it will get into the forward conduction mode, forward blocking mode. Then after that the forward conduction mode. And similarly, if you want to turn off, again it will come to the forward blocking mode, then after that the reverse blocking mode. But of course, anyway, in the forward blocking mode, which is nothing but the thyristor is turned off only. And the process of turning off is called as the commutation process. The process of turning off is called as a commutation process, and the technique which you are using to turn off the thyristor is a commutation technique. Okay, and the whole process is called as a commutation. Simply we can call as a commutation. The thyristor commutation is nothing but the process of turning off the thyristor. And then what are the conditions to get turn off the thyristor? One is we must apply some amount of the reverse biased voltage across the thyristor, as well as we must bring the anode current below the holding current. Okay, then only the thyristor will get into the turn off. So any one of the condition is not satisfied, then the thyristor won't be turned off. Because as I have mentioned here, even though, okay, if you are bringing the anode current below the holding current, the thyristor will not get into the turn off until unless you must apply the amount of a certain amount of reverse biased voltage across the anode and cathode. Then only the thyristor will get into the turn off. Again here, this turn off time is divided into two regions. One is the reverse recovery time, another one is the gate recovery time. The reverse recovery time and the gate recovery time. Right. So here, first we need to apply a reverse voltage for some finite time to give charge carriers time to be swept away from the outer P and N junctions due to the reverse voltage. Then once the charge has been swept away, then the recombination of the inner junction where sweeping is not possible. So the SCR will sustain forward voltage. Then we will say the SCR is turned off, right? So which means the time in which the excess carriers are removed, because to get the junction J to break down, so we have applied, we supplied some excess carriers, but in this case we have to remove that excess carrier so that the junction J2 again reform, so that it will block the flow of current from anode to cathode. Then the thyristor will get into the turn off, right? So to do that process, we must apply some reverse biased voltage, or we must apply the reverse voltage for some finite time, okay, to sweep out the excess carriers from the outer P and N layer, so that the thyristor will get into the turn off. And the time taken in which the excess carriers are removed from the two outer P layer and N layer is called the reverse recovery time. And what is gate recovery time? Then while the time in which carriers in the inner layer is removed due to the recombination is called the gate recovery time. That is called the gate recovery time. And here you can see we have just indicated different instant of times like T1, T2, T3, T4 and T5. So as you can see, at instant T1, the anode current becomes 0. Okay, the anode current becomes 0, but even though if the anode current is 0, okay, still it is not favorable. I mean, still it is favorable to conduct only, because as I mentioned here, not only just to bring the anode voltage to below the holding current. Okay, even though if you are bringing the anode voltage below the holding current, still the thyristor will not turn off. That's why here at instant T1, the anode current becomes 0, but the carriers are still under favorable to conduction, and the anode current will start flow in the reverse direction with the same rate, which means with the same slope, which is di by dt. And this reverse current will help to sweep out the excess holes from the outer P layer and the excess electrons from the outer N layer. Then at time T2, okay, so then some amount of the carriers have been swept away from the outer layer, then the reverse anode current start to decrease, and this the fast decreasing of the reverse current causes a reverse voltage across the SCR or the and then this terminal, the SCR or the thyristor terminals, and may therefore damage it. So to protect that one, we usually across the SCR we usually connect an RC element. Okay, the series RC element, which is also called as a snubber circuit. Okay, that we will discuss. When we are discussing about the protection of the SCR, there is a topic called protection of the SCR. Okay, because as we can see here, during the turn off process, because of increasing the reverse voltage across the SCR, the thyristor may get damaged. Okay, so to avoid that one, we usually connect a series RC element across the thyristor. Right? So these all are about the reverse recovery time and the gate recovery time. Right? So in the reverse recovery time, what will happen? Which means the name itself, it is saying the reverse recovery time. Okay. So because of the when we are dropping the anode current, okay, and to the zero, okay, so because that time maybe we didn't apply the the reverse biased voltage, okay, so still it will the current will flow in the reverse direction. Okay, because of the current flow in the reverse direction, there will be the reverse biased voltage also we will get. So because of that, the thyristor may get damaged. To avoid that, we are keeping an RC element across the SCR terminal. Right. So this is how the turn off characteristics of the SCR. And again here during the turn off characteristics, there are two different types of times are there. One is the device turn off time, another one is the circuit turn off time. The device turn off time is nothing but, of course, here to turn off the thyristor, okay, so we are using some extra circuit or extra some extra thing to turn off the thyristor, because as we know, this is the semiconductor is a semi-control device, not the full control device. So the turn off process we cannot control by using the gate signal or by using any other terminal of the SCR. Okay, so you have to connect some extra circuit that is called as a commutation circuit to turn off the thyristor, and the time taken to turn off that circuit, okay, is called as a circuit turn off time, and only the device, then that is a device turn off time. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.